Hi there, and welcome back to Severe Weather with Mr. CB. In this video, we're going to be talking about ways to measure instability within the atmosphere. We know that there's one that we've talked about quite a bit, CAPE. So, just a reminder of what CAPE is, even though we've talked about it, I'll just say it again. It's the area that's enclosed between the LFC and EL on our soundings. So, and it's in between the environmental temperature line and the parcel trace. So it's that area enclosed. And it's the amount of energy that we have available as the parcel is accelerated upwards. Now, keep in mind that it is stands for convective available potential energy. It is potential energy, so it's important to note that sufficient CAPE is not going to guarantee that we'll have storms. And the unit of CAPE is joules per kilogram. Now, here's how CAPE is actually calculated. It's an integral, which, if you know your calculus, you will know that is associated with area under a curve. And so, an integral like such as this, that is from a starting point to an ending point, is going to help us calculate a specific area. And here's what these different variables mean. We have the TVP, which stands for virtual temperature of a lifted parcel. Now remember that virtual temperature is a correction. It helps us to better represent how a parcel would respond in an environment that does have moisture because there likely is some moisture. So what that is really saying is that our normal parcel trace, we follow the dry adiabatic collapse rate at the beginning, but there actually will be moisture at the surface generally. Um, so that's why we have this little correction that moves it a little bit over. Here is the virtual temperature of the environment. That's what TVE is. We have PN, that's the end of our integral. That's the pressure at the equilibrium level. And then PF is the pressure at the level of free convection. So we go from PF to PN. Those two are the bounds of our integral. And then RD is just a gas constant for dry air. And then you hopefully know what D and P mean. All right. What affects CAPE? Well, climatology, depending on where we are, is going to affect CAPE. So, obviously, there's going to be certain regions that are typically more associated with instability than others in certain seasons as well. Method of lift, what is the way that the parcel is being lifted? And then just other environmental factors. But here are some levels of CAPE and what stability they're associated with. So ML, we'll talk about that, what that means later, because there's different types of CAPE. But if we have zero, that's stable, 1 to 1,000, and you can read that. Like I don't need to say all those, but um, you obviously the greater the CAPE, the greater instability that we have is the point. So types of CAPE. Here are some types of CAPE that we're going to talk about, and there's also parallel to this types of SYN, and we're going to talk about that in a second. But we have surface-based, mixed layer, most unstable, forecasted. We also have normalized. We'll talk about that. All right, CAPE shape. So the shape of the CAPE that we have on our sounding is going to associate with what level of updraft acceleration we are going to have taking place. If we have tall, skinny cape that's more like, I guess if I were to draw it, um, cape that's like this region right here, that is going to be slower updraft acceleration. Whereas if we have cape that's short and wide, more like that, this region in here, maybe they have the same area, but the shape of it um, is going to in this case, have faster updraft acceleration. Sin. Now, if you remember sin, that's the other area that we have on our SKU. This is the area that's enclosed by some originating level to the LFC. And it's the amount of energy required to lift the parcel to the LFC. It's really energy that the parcel has to overcome to get to a certain height. It's measured in joules per kilogram. The calculation for this is very similar to CAPE, but this time we have a negative integral. And the reason why is because it's energy that has to be overcome to get to that level. Um, Most of these variables are still the same, although instead of going from PF to PN, we're going from PI to PF, but that PF is still the same value. So the PI is the pressure at the originating level, and PF is the level pressure at the LFC. So now let's talk about surface-based CAPE and SEN. So surface-based CAPE is we this surface-based is what we usually associate with the SKUT. It's a measure of instability at the surface, total potential energy available to a parcel originating at the surface being lifted to the LFC. Surface-based sin is the amount of energy that a parcel has to overcome to reach the LFC. And it's energy that's working against parcel, which is why it's negative. Then we have mixed layer cape and sin. That's what we had saw before, which was ML cape. This is the most widely accepted, and you'll oftentimes in the sounding at below in the table have a list of all these that you can see and compare. But this is the most widely accepted, and it looks at an average of moisture and temperature throughout the planetary boundary level layer. Um, and remember, that's the layer that's still influenced by Earth's surface. So it's mean potential energy conditions available. It's average. That's the key thing. So it's the mixed layer. Um, Mean potential energy conditions available to a parcel of air located at the lowest 100 millibars atmosphere. This is what we see when we are looking at a mesoscale map such as this. 0 to 3 kilometer cape is the amount of cape in the lowest 3 kilometers. Sometimes we can have specifically this lowest. Mixed layer sin is analogous to the mixed layer cape. Less sin is associated with less blue on this mesoscale. Um, and there's going to be a higher chance of thunderstorms because there's less energy that the parcel has to overcome to get to the LFC. Most unstable cape is the total amount of potential energy available found in the most unstable parcel. Now, the thing about this is the typically going to be the largest value of CAPE, and you know, people will share this when they're wanting to share what instability we have because that might get maybe the most clicks or views on whatever platform. So this is total amount of potential energy found in the most unstable parcel. So that's why it's called that, within the lowest 300 millibars of the atmosphere. It can be useful for elevated convection, but other times it can overestimate sometimes. The LPL is the lifted parcel level. It's the height where this most unstable parcel is, and it's the area where the largest cape is elevated. Forecasted cape and sen utilizes forecasted surface characteristics. So this is just which characteristics we have. It's basically calculated by using the characteristics of, what am I trying to say? Of the future forecast. So it's more of a um, forecasted method, which that's obviously why it's called that. So, all right, then we have N cape and D cape. Normalized cape is cape divided by the depth of the buoyancy layer. Um, and this is basically what's helping us to um, where we were talking about the cape shape. Normalized cape is telling us the shape in terms of a number, pretty much. Tall, narrow cape, I already said, has weaker partial acceleration. Short, wide cape, stronger. D cape or downdraft cape is an estimate of potential strength of the rain-cooled downdraft. It's how much energy there will be in the downdraft of a thunderstorm. Then we have another way to measure instability is, aside from looking at CAPE and SIN, is surface-based lifted index. It's the parcel temperature subtracted from the environmental temperature, specifically at 500 millibar. The more negative number that you have, the more instability. Then the last thing we'll talk about is the Showalter index, SI. It's the difference between the observed temperature at 500 millibar and the temperature of an air parcel that's lifted adiabatically from 850 millibars to 500 millibars. The same thing with the other index, the greater negative value means more instability. It's useful for situations with cold pools below 850 millibars. So you can see here what Showalter index that we have can tell us what weather that we might end up having. 3 to 1, just rain showers, maybe thunderstorms, thunder showers. And then the more negative number, the more chance of severe weather we have. Thank you for watching.